Okay, in Chapter 10, we're going to be talking about area. This chapter we're going to start out with, screen messing up there. We're going to start out with the area of a rectangle and the area of a parallelogram. Now notice in these theorems, the area is exactly the same for both a rectangle and a parallelogram. The difference is, in a rectangle we have all right angles, so the height is just one of the sides. But in a parallelogram, there are not right angles, and so we have to look for the altitude. And in this case, in this theorem 10.2, they have the altitude that height h is drawn to the side b, and that's the base. So the base can be any of its sides, and over here to the right we have with a parallelogram that we're looking at two different ways we could calculate the area. On the left side, the base is the bottom side, and the altitude is drawn to that side. So that would be, I would be using the bottom side as my base, and that altitude is the height. If we look at it as the left side being the base, then I would need the altitude to be drawn there, and sometimes the altitude is drawn on the outside of the parallelogram, so it just has to be drawn to the line that contains the base. So if I was going to use the figure on the right, I would need to use the left side and then the altitude, whatever that measure might be. So my example 1, both of these are parallelograms. We're given in A both sides. I need to decide which of those I'm going to use as my base, and so I decide that by where my altitude is drawn in. So the altitude 4 inches is going to be my height, and it's drawn to the side that's 5 inches, and that will be my base. So my area will be the base 5 times the height 4, which is 20. Now when we're doing area, we need to include our units. So I had inches times inches, which will give me square inches. So I can either write that with inches with a little squared in the exponent, or I could say the area is 20 SQIN. That abbreviates for square inches. Either way is fine. But make sure you include your units when you're doing these problems. Okay, so part B is another parallelogram. I'm given a side that's 4.6 centimeters and a side that's 2 centimeters. I need to decide which one I'll be using for my base. So I look at the altitude, 3.5 centimeters. That's my height. It is drawn to the line that includes the bottom side, and so that will be my base. So 2 centimeters will be my base. So my area will be 2 centimeters times 3.5 centimeters. So that's going to be 7 centimeters squared, or square centimeters, whichever way you prefer to write it. Okay, I want y'all to pause and try this quick check 1. Find the area of a parallelogram with base 12 and height 9. Okay, so hopefully you stopped and tried this problem. We don't have a picture this time, but they give us the base and the height, and so we don't need a picture. So my area is just going to be 12 meters times 9 meters. That's going to end up being 108 meters squared. Or square meters if you prefer to write it that way. Okay, so now this one's a little bit different. We've got a parallelogram drawn here on the left, and we have several different kinds of information. We have both sides. The bottom side is 10 inches, the left side is 13 inches, and we have an altitude drawn in 12 inches. What they're asking me, though, for parallelogram ABCD, find CF to the nearest tenth. So we're trying to find this side CF. All right, so what I'm going to do is first find the area using the base that has the altitude drawn to it. So I'm going to use 12 as my height and 10 as my base. So that's going to give me 120 inches squared. Okay, Now I know that another way of calculating the area is to use the other base and its height, the altitude that's drawn to it. So the side that's 13 inches has the altitude x. That's the height for that one. So I could have written in 13 inches times x inches. But I don't know what x is, which is why I use the other. But now I know that the area has to be 120 square inches, and it has to be the same regardless of which base I use, as long as I'm using the proper height with it. So this is going to tell me that 13x has to equal 120 inches squared. So I'll just divide both sides by 13 to find out what x is. So it's going to be, x is going to end up being about 9.2 inches when I round it. So, and this is inches because I was dividing inches squared by inches. So that just leaves me with just inches, not square inches. So that's my CF. Okay, pause and try quick check 2, which is pretty much the same. They just don't have the picture drawn. Okay, hopefully you tried that and feel like you got it right, but let's go over it. A parallelogram has sides 15 centimeters and 18 centimeters. The height corresponding to a 15 centimeter base is 9 centimeters, so that means I can go ahead and calculate that. The 15 centimeter base was multiplied by the 9 centimeter height. So that's going to be 135 inches squared. It will be the area of that parallelogram. And now I'm trying to find the height that corresponds to the 18 centimeter base. So that area, which is the same, will be 18 times the height that I'm looking for. So I know that 18H has to equal 135. So then if I divide both sides by 18, I should get that the height is, and I'm rounding to the nearest tenth, I believe, it's about 7.5 inches. Oh, I'm centimeters this time. Okay, continuing on, we're going to be looking at the area of a triangle. So that's the third theorem, and I didn't put the picture on here, but the area of a triangle is just 1/2 times the base times the height. Basically, a triangle, I could draw a whole parallelogram in, and that triangle would be half of it. So I'm using the area of a parallelogram times 1/2 because I could draw any of these triangles as half of a parallelogram. So again, the base, I have to pay attention to what I'm going to use as the base. It can be any of the sides, but it has to have the corresponding height drawn to the line that contains it. So sometimes that's within the triangle, sometimes it's not. In the picture that we're given here on the left of example 3, I have this side of the triangle is 10 feet, and then I have 4 feet outside the triangle and 6 feet here. So what I'm going to use is the 6.4 feet as my height, and the 10 feet as my base. All right, so that's going to be basically 5 times 6.4. That's going to give me about 32, and that's in feet squared. Excuse me. Okay, so it's important just to make sure that you use the base and then whichever altitude is associated with it for your height. So pause and try quick check 3 just below this. Okay, on this one we have a right triangle, so you could either use 12 centimeters as your base and 5 centimeters as your height, or you could look at it sideways and think of 5 centimeters as your height and 12 centimeters as your base. But we don't have any altitude drawn to the 13 centimeter side, so we can't use that side. So this will be 1/2 times, I'm going to use 12 for the base, and then times 5. So that will be, half of 12 is 6, times 5 is 30 centimeters squared.
6.
Okay, now let's look at a real-world problem that has to do with these areas that we're working on. Here we have a building drawn at the bottom left, and this problem says when designing a building, you must be sure that the building can withstand hurricane force winds, which have a velocity of 73 miles per hour or more. The formula F equals 0.004 AV squared gives the force in pounds exerted by a wind blowing against a flat surface. A is the area of the surface in square feet, and V is the wind velocity in miles per hour. So how much force is exerted by a 73 mile per hour wind blowing directly against the side of the building shown here? So if we're going to use this force equation, I'm going to need to know the area of this building, the side of this building where the wind's blowing, and I need to know the velocity which I was given, which is this 73 miles per hour. So I'm going to calculate the area. The way I'll do that, because these are more than one figure, is I'll find the area of the rectangular side, and then I'll add the area of the triangle above it. All right, so the area of the rectangular part is just the base times the height, which is 20 times 12. So that's going to be 240 square feet.
Yeah.
All right, that's the rectangular part. Let me erase this over here. Okay. So this is 240. Now the area of the triangle will be 1/2 times the base times the height. And in this case, the height is the 6 feet that is drawn in there. That's my altitude. The base is this side, which I know is 20 feet because that's a rectangle on the wall underneath. So this is going to be 1/2 times 20 times 6. So let's see. So 1/2 of 20 is 10. 10 times 6 is 60 square feet. Okay, so the area of that side is just going to be 300, or the side of that building. Let me put little subscripts. So my total area will be just that A1 plus A2, which is going to be 300 square feet. Okay, so that's part of the answer, but not all of it. They want to know the force that it's going to withstand, so we have to plug that back into our equation. So the force will be 0.004 times my area 300 that I just found. Elijah keeps coming in and out. And then times my velocity squared. My velocity was 73 squared. Now, if I look at the units when I'm multiplying these things, it ends up giving me a force in the units that I need for the force. But we're not too concerned with the units for force right now. So when I multiply all of this out on my calculator, I end up with a force that's equal to about 6,400 pounds. It's 6394.8. So that's approximately, if I round it up to 6,400, that's about 3.2 tons. 3.2 tons. So a ton is 2,000 pounds. So if you just divided the 6,400 by 2,000, you would get 3.2. Okay, now the quick check question asks us, suppose the bases of the rectangle and triangle of the building are doubled to 40 feet. So instead of the 20 feet, now we're going to have 40 feet. And they're asking, how is that going to change the force of the wind? So if we did that, our area of the rectangular part would be 40 times 12, which is going to end up being 480 square feet. And then the area of the triangular part would be 1/2 times 40 times 6. So that would end up being 20 times 6, which is 120 square feet. All right, so my total area of the side of the building there would be those two added together, which will give me 600 square feet. Now, in the last problem, let's go back just real quick. The last problem, our area was 300 feet squared. So in this problem, this area is double. So since I'm doubling the area and my force is that 0.004 times the area times the velocity squared, well, this velocity squared didn't change, this number didn't change, but the area was doubled. So what's going to happen is the force will be doubled. Because we're just like we're multiplying that equation by 2. Now, we didn't have to actually give what the force was this time. We just were trying to figure out what would have happened to it. So since my area got doubled and I would be plugging that into the equation, it's the same thing as if I had multiplied the other force by 2. All right, good luck on your homework, and I'll see you in class.